Welcome. I'm Thomas Hall, Executive Director of CleanStart, and this is a CleanStart perspective. CleanStart perspectives are brought to you by our supporters over at SMUD, Chico Start, Fresno State, Witten Law, Moss Adams, and River City Bank. All of these organizations come together to support entrepreneurship in the Central Valley, and a lot of them specifically focus on technologies that are driving the energy revolution. River City Bank is a large financer of clean energy projects. SMUD, they have their 2030 goal. Fresno State is funded by the CEC and the Wet Center at Fresno State is part of the Blue Tech Valley Innovation Cluster that we're under. Chico Start has had us go around and talk about clean energy to everyone. And Witten Law and Moss Adams are here for your early entrepreneurship needs. And with that, I'm excited for the guests that were coming on. We've talked a lot about batteries and we've talked a lot about, electric vehicles, storage, and all these things. But when you put all of it together and you make a system, there's a lot of other parts in it. And a slight increase in, battery capacity, doesn't have the same impact as some other things do. Because when you have a battery and then you have to turn it from DC to AC or from AC to DC going back into the battery, there are some losses in there. And those losses are, compounding. So when it comes to innovations around storage, the grid, and energy delivery, there is a lot of space for improvement. And these improvements are very significant because they kind of work exponentially in there. So with that, I'm going to welcome our guests, Edson Perez of Parawatt. Parawatt is a startup that he's working on, and he's going to share us a little bit about, the technology, where it kind of sits in the ecosystem, and where they're kind of going with it. So with that, I'm going to welcome Edson Perez to share his screen, and I'm going to stop share and
Thank you so
take it away.
much.
And if you don't mind, during your presentation, do you mind if I jump in with questions occasionally?
No, that sounds great. I have a short presentation, but then a few appendix slides that I could jump to answer any questions,
All
depending
right.
on where we want to take this.
Okay.
But yeah, thanks, Thomas and Gary and Myra and everyone at CleanStart for the invitation. I really appreciate it. Maybe before jumping into the company and the technology, do a quick introduction about myself. So yeah, my name is Edson Perez, and my background and my career has kind of mostly been in actual policy making and regulations. I work with in the state legislature for different legislators for around 7 years on all kinds of policy issues, including energy, natural resources, and just crafting frameworks under which companies can operate and succeed. And then I did business school, and there I really focused on clean energy and clean tech entrepreneurship and helping startups enter markets and scale and deliver their innovations. And now still working as an advocate for clean energy companies. I represent over 100 clean energy, clean tech companies in the policy space, but also directly advise them on how to enter, once again, just markets with a focus on the California market. As we know, the energy space is very interconnected with government. It's very highly regulated. So a lot of times, market entry is very tied with government policy. But so that is all beside what I'm also working on now, which is this company Parawatt. And with that, maybe I'll jump into it. See if this works. All right, do you see my big screen? Great. So going into this company, this startup, first of all, my name is Parawatt, and we are seeking to optimize efficiency for next generation power systems. So the big problem that we're tackling is power losses, as Thomas alluded. So the big problem here is that about 15% of power is just wasted through power losses as heat and other types of losses across all energy systems. So both in the delivery of power from where it's created to where it's consumed, but just there's in a lot of different points. This results in around $450 billion per year that is just wasted because of these power losses. And a lot of it happens in these points of power conversion. like Thomas alluded, this is when power is converted from AC to DC or vice versa. And when voltage is changed, is stepped up or stepped down. This happens sometimes hundreds of times before energy gets to where it's finally consumed. And it often happens in these just really small circuit boards and these power boards, kind of like you see here on the lower right. And a lot of those power losses happen because of magnetics. So here's a focus, for example, inductors, which are these donut shapes here. They heat up very quickly, and their energy is lost as heat, and other types of power losses. So that's where a lot of the loss is happening. And before diving into why, I want to emphasize that again, these magnetics and power losses are happening everywhere. Just in an office, just everywhere where there's power, there's a lot of power conversion. Computers, printers, lights, and then along all these big power consumers like solar inverters, EVs, data centers, consumer products, electric motors. So these are all point that there's a lot of power conversion happening here, a lot of power losses happening here. And just to put another visualization on this, this is a data center rack. So in each power unit in a rack, there are countless of these, sometimes dozens of these in each of these. And these inductors heat up and again, lose a lot of power there. And so our solution here, oh, before going into the solution, I think I would emphasize that the reason why this is happening, why this has been improving a lot over decades, is because these magnetic materials haven't seen real innovation in decades, over 30 years. Making a new material itself is very difficult, right? A material that can be stable over time and deliver the same performance. And so because of that, there hasn't been a lot of innovation in this space. And so these magnetics are very big, bulky, and lose a lot of power. So what we're working on in Parawatt is a new magnetic material that would deliver up to 10 times higher efficiency than the materials that are out there in the market right now. And we can deliver this at a competitive cost because the material that we're working with is made up of commodity raw materials and is made with a simple manufacturing process that's comparable to how you would make other materials that are in the market right now. And we're able to deliver this innovation that again is there's not a lot of innovation in this space because we're partnering with a national lab. So the Department of Energy is investing in a lot of very fundamental research, and we're licensing a patent out of a national lab. And this is innovation that has been worked on over the past 10 years to get to this place, to get ready for the market. I think that's what makes us, special, that we have a license on this innovation. And this is just laying out a little bit more about what each market is. And this big market that we're in is that of soft magnetic materials. So the magnetic materials that we're making, they are soft materials, which is different than permanent magnets. Our magnets get magnetized when current flows through them. And that's what makes them different from the permanent magnets, which are often those are the kind of the rare earth metal magnets that you hear often about. So in our market of soft magnetic materials, again, it's really big, $115 billion, and it applies to all these different power systems. And I want to emphasize here that each of them see efficiency a little bit different, like what they value in efficiency can be a little bit different. For data centers, they can heat up a lot and they spend a lot of money on cooling. So more efficiency there means less heat, and that means less spending on cooling. For solar inverters, heat can be a big deal, but size can be an even bigger deal. We're showing here a large inverter for a large solar farm, but a lot of inverters are microinverters that go on people's homes, and their ease of installation is very important. So having very smaller magnets can make their power electronics much easier to install, and that can save a ton of costs for the company and the customers. So they can really value size. similar with EV chargers. Now, electric motors is a whole nother deal. They use soft magnetic materials in tandem with permanent magnets made of rare earth metals to transform electric power into mechanical power, right, to make the car go. And if you make much more efficient soft magnetic materials for the motor, then you need less rare earth metals. And you can also make the motor a lot smaller and lighter. So each of these markets see efficiency again a little bit differently, but we can shape our materials in all these different ways to benefit each of these. And just a little bit about kind of our roadmap and where we are right now. So before 2025, 10 years in the making is what the lab has been working on, doing 10 years of research. And right now we're in the tech transfer phase. So we're licensing this patent from this lab, and we are starting to develop initial samples. We're talking with a lot of customers, and they're very excited about there being a new material in this space, and they want to test their samples. So we're going to start making samples. And we're also starting to do our own IP development and working with the lab to co-invent kind of new offshoots off of this new material. Because it's, again, what it delivers is very application dependent. So we'll improve upon the material depending on the application and the customer. After that, we plan to develop more IP, do actual customer pilots because they have to do thorough testing on these materials because they're going to be in machines that work for a long time. And then, at 2028 and over, we plan to scale up and deliver these scale. So I'll stop there as kind of like the gist of it, but I'm happy to get a little bit more into maybe power conversion or the company side of things or any other things if you guys or others have questions.
First off, it's kind of exciting. I mean, I don't think people understand, how kind of interesting this is. I remember growing up and seeing the little like circles and thinking they look like Fruit Loops with wires around them. But, they play kind of a really big role. You mentioned that loss on electricity, and that's due to efficiency things that you're directly kind of addressing. Now you listed, four initial kind of markets there. You talked about servers, you talked about solar, you had the grid on the other one, but with the big boom in AI, are you seeing a lot of interest in your technology?
Yeah, definitely. And I think that speaks to kind of diving a little bit into why the magnetics are very in high demand right now. New magnetics, better magnetics, is because in like data centers are trying to become more efficient. I think we hear a lot about semiconductors and that there are a lot of improvements there. Well, semiconductors are key in power conversion as well. And the advances in semiconductors are helping all these power conversion systems become smaller and become more efficient. But semiconductors work hand in hand with these soft magnetic materials. And as the semiconductors become smaller and more efficient, the magnetic materials still are big and bulky, and they can't be made smaller and more efficient. And so they're becoming increasingly the bottleneck for efficiency gains for big power consumers like data centers. And so there is a lot of demand in this space from that market and other large consumers like EVs, for example. And EV chargers consume a lot of power, so they care about this too a lot.
I think that's important for, people to focus on is the bottleneck. Making bigger batteries doesn't really help if there's a bottleneck there. The increase in the efficiency can take what we already have and make it more, and we're able then to go and do more with it. Now, as far as, semiconductors and the efficiency on it, you mentioned that you're in the step process of getting kind of materials to go out there and test it and validate it. What's the kind of process for validating a deep tech solution like this that you're going through? I think if I recall, you're working with a couple different universities around to de-risk the technology, but I was hoping you could maybe go a little bit more into that.
Yeah, that's a good question because deep tech is, I think, doing the testing and the customization. It's different for every deep tech, but it can be very complex, right? With a new material, we can go a million different ways in terms of the shape that we make it in, size. We can tweak the composition, and we can tweak then not just the material, but like what system it's in, and there's different frequencies that they can operate in, and it just a lot of different applications and voltage that can be applied to it. So I think all these different levers to pull, it means that there's going to have to be a lot of testing that we do in a lot of different applications to try to find where, one, it fits best, but then two, how to improve our material and its performance for that specific application.
So when
Yeah.
you talk about specific application, how much of this testing do you need to really involve like the customer and the use case for it? If you make a solution for, data centers, is that now going to be able to easily transfer to EV chargers or solar inverters? How much of a, I guess, specialized testing and de-risking depends upon the customer's use?
I think there's gonna always be transferability. I think what's another part that's interesting about this industry, it's that the data center developer, say the Google or Microsoft, that is putting the whole thing together, they're not necessarily working on the magnetics, right? Or even the power electronics board. They work with other companies that take care of that for them. Similar with EV chargers. And so these third-party companies, which are the power electronics designers, we'll call them. It's kind
Mhm.
of like their industry. They'll make transferable power electronics and source magnetics for those that they can then serve different end industries like these data centers,
Mhm.
inverters, EV chargers. So it's in their interest and in ours as well to make things transferable for different industries. Now, there are going to be some power electronics. Again, a data center can have dozens of different points of power conversion, and within those dozens of different magnetics. And so some of those will be very similar to those we used in EV chargers, and some of those will be very different, right? Depending on just how power is being used in that specific data center and or that specific EV charger. They're also inside of electric vehicles themselves. I guess not a very satisfying answer because there's just so much diversity, but I think there's a lot of transferability, but also a lot of customization that needs to happen.
Yeah, so yes to everything on it there. Now, so of the kind of, the EV, the charger, the data center. There, it also sounds like a lot of time, you're not directly working with the person building the data center. You're working with the person building the circuit board, the person building, the hardware that's inside the inverter there. Now, can you can you tell me a little bit about maybe how those spaces might differ from other commercial spaces? Are they right there looking at just like exactly the bottom line of the cost on everything, or is there pushes for increased performance?
Yeah, that's a good question. I mean, I think that they all look at both, but maybe the emphasis is a little bit different. So, like for the end customer, they don't know typically what goes into the power electronics or magnetics. They just say, I want my end system, if possible, like to be as smaller as possible. And I want it to operate at these voltage levels. And maybe they might even know like at these frequencies, they have these like kind of bigger metrics. And I want it to deliver this much computing power kind of thing, right? That's more what they would care about. And then they will give those specifications to the power electronics designers. And so the end customers care about, I think, cost, but maybe in AI data centers, more so performance, right? Like more compute, less heating up. I guess on the cost side, if you can save money on the cooling systems, they would like that. And then they give that to the power electronics folks, and then they just have to meet those specifications within whatever budget they're allocated. So the work that we have to do is kind of twofold, right? We
Mhm.
have to work with the power electronics designers to tell them, hey, our technology is here and it's ready, and just put it in your repertoire. when you're working with these folks, and let's test it with you guys and in the systems that you have that are applicable to many industries. So we work on like the tech side of things with the power electronics designers, but then we also go to the end users and say, hey, having better specifications is possible because of these new magnetics. So like even if you don't know enough about magnetics, like we can talk to some of them and say, you can ask for more, and then we can deliver through this third-party person and create that market pull. So we create the market push through the on the actual tech through the power electronics designers and create the market pull with the end customers. So we are doing both and we have to do both.
Sounds like a lot like, because you mentioned the semiconductors about their impact and how they're impacting the market of, being able to be smaller and more efficient, and then opening up an entire new range of possibilities when it comes to computing, charging, and power. Now, how much can you share about, the new material that you're making and what it consists of? Is it a common material, or is it going to be something difficult to find?
Yeah, I mean, I'm happy to have individual conversations with folks, but about more specifics. But I think on the big picture, to your question, we're using commodity raw materials for our product. I think that's one of the main value propositions because there are some kind of more complex soft magnetic materials that have come out in the last 10 years or so, but they're using much more rare materials
Mhm.
that are harder to source, and because of that, and also use a lot more like difficult manufacturing processes, and because of that, they're very expensive to deliver similar performance as what we're trying to deliver, but we're doing it with commodity raw materials. Now, all of these soft magnetic materials have typically an iron component to it, so ours does too. But I think
Mhm.
other materials that are coupled with it are and how the composition is made
So you
is where the
mentioned
difference is.
manufacturing in there, and you guys are, of course, a bit before where you're getting into scaling up and manufacturing. How much of the design of your project or your product, how much of your design of the solution of this is keeping in mind what it might look like when you have to scale and have a manufacturer?
Yeah, I think that's key, right? Like we have to be confident enough that we'll eventually be able to do this at scale to start in the first place. I think that's part of what's key in the innovation itself that we're patenting is it's an innovation to make this material in bulk. And so it's proven that we can make, quantities of this. Now, the process itself to make our materials is fairly simple. I guess without getting into the weeds of that, it's established processes. Like we can actually contract it out to facilities that exist nowadays because the secret itself is maybe not on the process. Again, these are things that other people can make for us. It's in the composition and then the specifications that we put on that process. It involves, it can involve like having current flow through these materials to like sinter them in a specific way. It can also involve other processes like hot pressing our raw materials. So we're confident that this is how you make other things that are already in the market and are durable. So the process itself is replicable and is scalable. Now, whether our novel materials will once we made and tested and used for years, whether they will like maintain their full integrity for long periods of time, that's something we still need to figure out. It's part of the process here too.
Yeah, I'm just double
Works.
checking that it's not like a fusion reaction that requires a bunch of perfectly cylindrical gold pieces in it.
Yeah, exactly. No,
That,
and I think that's part of it that it's not that. So we that's why we like jumped into it. Yeah. I should mention, we, CleanStart Sacramento, we have UC Davis facilities here. We were talking with UC Davis about potentially using some of their lab equipment because again, this is we're using raw materials that are commodity and we're using processes that already exist.
Hmm.
So the IP is somewhere else, so we could potentially, start partnering close by.
Will, I saw you had your hand up. Did you change your mind or?
No, I just didn't want it to linger there. Just two questions. How far out are you guys from having a prototype like that, you can put in people's hands for the material?
We have a prototype already. So the lab that we're working with has made dozens, maybe more, of different prototypes and has done some testing, at least on the fundamental like magnetics to physics level. And so we have some prototypes that are like this big. I don't have one with me right now. Yeah, but we haven't made our own outside of the lab quite yet. Again, we can use other facilities and whatnot. So we can do that, you know, soon. We're planning to, but the prototypes that are made in the lab can already be tested in like, say, a power electronic circuit board, and some of that has happened already. But we still need to do it ourselves outside of the lab, prove that we can do it, and then do some testing in-house ourselves with small power electronics to then do some testing with customer partners. So we're already talking to.
So going on that, what is in the next, I guess, 6 months for Parawatt? What are you guys looking to accomplish? What are your kind of short-term plans for growing the company?
Yeah, it's a good question. So we are actually we're in the middle of fundraising right now to do just what I mentioned, to do our initial like Parawatt prototypes and our testing with these facilities that, with these other folks that we're already talking to. And so we're seeking an initial kind of angel round
Hmm.
to start performing those, to start doing those. And the goal is to get those angel funds for in the next, where we actually got our first commitment last week, which is great. And because we started just a few months ago, I think it shows that there's a lot of demand and traction in the space. So we just need to raise a little bit more funds, and then we'll do those prototypes, do that testing in-house. We think through the end of this year, and then we'll get enough data to not just excite customers because there's something new and exciting, but to show them like we can actually perform all these things for you, and then they can do pre-orders and things like that, and we can raise a big round, ideally end of this year, beginning of next year, and then do those like more comprehensive pilots at that time.
Okay, so kind of with that, what are some, I guess, from your final thoughts, what are your kind of forecasts for this area of the clean tech revolution?
Yeah, I think there's a ton of opportunity in the energy transition. Now, I know things may seem rocky, at least in the US, for energy transition and clean tech. They are, but the larger trends are still there, right? Electrification is still a huge thing. Demand, electricity demand is still going to skyrocket. It was already going to skyrocket before AI fully came into the picture, right? Because EVs are increasingly going to be adopted and continue to be adopted. And there's electrification of just about everything where there's power. And now there's the data center demand. So I think anything in the power space, when we're also trying to clean up the types of electricity that's used, right? So there's a ton of opportunity here to help meet that demand and help control that demand, both in the size of it, right? Like what we're working on is efficiency, just preventing, like maybe reducing the demand a little bit or substantially, depending on the application, to help. But then you can also, I think, what another thing that's exciting is controlling how the demand works through just software and energy devices at the distributed side, at the behind the meter side, right? Like these
Hmm.
home batteries, these EVs. These are
Yeah.
energy devices that can be controlled, how an EV is charged can be controlled, how a home batteries charge and discharge can be controlled to benefit the grid the best. Power conversion happens across all of that, so we're just going to have more and more of that, potentially more power losses or power gains if we use better magnetics. So just a lot of exciting, I think, things in this space, and maybe while keeping in mind all the stuff that's going on, I think we should also have the bigger picture in mind still.
And I just had one more question that popped in my head. What are your, definitions of success for this? What are your kind of goals for improved efficiency? And I don't know if you can make an equivalence of this, but what is kind of like the cost per saved watt or kilowatt potentially with that efficiency?
Yeah, it's a good question. I think we'll have to add that to
Test it,
our
part of the
success metrics.
techno-economic analysis.
Yeah,
Go forward
exactly.
on it.
We'll add to that. I mean, I think the $450 billion per year that I showed initially, it's just it's just a fraction. We need to do better calculations about how much we can really save. But 450 billion is 15%. I should have done the back of the envelope calculations, but a 1%, there we go. I mean, it's easy. 1% of that is over $4 billion that could be saved. Now, this is worldwide, but it's still very substantial. And
Mhm.
again, it's just a fraction. It's about like the energy loss itself. A lot of cost goes into cooling when things are heated up or heat up, right? So we can save a lot of cooling costs. We can save a lot of, again, installation costs and all these other things. And probably most importantly, we can help save the grid from blackouts, right? If
Mhm.
we reduce
Oh yeah.
demand, if we reduce waste. So I think the impact is potentially huge, right? Of really getting this technology right, and it's just applicable just about everywhere. So I think it can do a lot of good.
All right. And with that, I think we'll wrap up unless we have any questions from the crowd. No? Okay. First, I want to give a big round of applause to Edson. Thank you for taking the time out of your day to join us and talk about, power conversion. It is a little, wonky, but it's incredibly important when it comes to the future of the energy transition. And I also want to thank our supporters, SMUD, ChicoStart, Fresno State, Witten Law, Moss Adams, and River City Bank. They are sponsors of our clean tech perspectives, and they help keep us going. Also want to encourage you to join our next perspective, which is talking about AI and how you can use it as a tool to increase your efficiency. Later, we'll have William sharing his entrepreneurship journey and what he learned from it. And later this on the same day, we'll have a discussion that'll also include Edson around alternative communities around batteries, but it'll mostly focus on can we get efficiency gains in the technology that doesn't rely on necessarily making bigger batteries. So with that, I'd like to thank everyone for attending. Make sure that you follow us through our channels and hopefully see you at the next ones. Bye, everyone.